Hey, did you miss the Navigate Twitter as a Scientist training on March 22nd, 2023? No worries, we recorded it for you, and you can still access the recording. Just follow the link in the episode show notes to get your hands on the recording. Only for 36 euros, so you are basically saving a lot of money. 1 hour, you get all the tips and tricks of using Twitter as a scientist. Go ahead, follow the link in the show notes. You're welcome. Hi everyone, I'm Pranoti, your host of Under the Microscope, and today we have with us, by the way, 201st episode, so very excited about this one. Today we have with us Julio Terra, who is a postdoctoral associate at EPFL Lausanne, which is in Switzerland, and Julio also has an amazing office view, and that is the Lake of Lausanne. So welcome, Julio. How are you?
Thank you. With the Alps on the background, which is beautiful. Yeah.
And I just realized I went all German and turned the J into Y, and instead of continuing to call you Julio, I started calling you Julio at some point. So apologies about that.
It's fine. I'm used to Julio as well all the time, so
Okay. And now that you are in Europe, I think you might hear this very often that you are called Julio and not Julio. So I apologize on behalf of the German-speaking people collectively. All right, let's get cracking. So, Julio, Julio, tell me about your research. Please tell us about your research in super simple words, please.
Yeah. So the motivation of my research, number one, is green chemistry. So what we want to do is we want to make chemistry more sustainable and also safer. And we want to produce less toxicity. So those are basically the basic ideas of green chem. And then we can approach green chem throughout different, we can use different tools to achieve green chem. And what I do specifically is catalysis. So I design nanoparticles that can be used to make processes, more sustainable and greener, because catalysis is in almost everything that we do. Almost chemical product is made through a catalytic process. So if we change a little bit the catalyst, we can change a lot the process. We can, use less energy to make the products. We can, have higher selectivities, produce less waste. We can change completely the products that we have. So, small tweaks in catalytic systems, they can make big differences. So this is what we try to do. We try to, find where we can change the catalytic systems so that we change the reaction as a whole and we make them greener in some way. Yeah.
Mm-hmm. Mm-hmm. Okay, that's interesting. So when you say greener reactions, are we talking about making the renewable energy reactions more efficient, or are we talking about some other field, so not batteries or not renewable energies, and making the reaction, like the chemical process, more green? Like what do you mean when you say green chemistry?
Yeah, so it's a very broad theme. So it depends on what exactly you do. Like in my PhD, I worked mostly on reactions that are important for the pharmaceutical industry. It's an industry that is highly wasteful. If you think about, if you look at the E factors, which is basically how much waste is formed per product. In the pharmaceutical industry, you have like 90% of waste and 10% of product usually. So it's nonsense. It's because usually the molecules, they're very specific because they need to play very specific roles. Mm-hmm. So putting them together is not that easy. So usually you need many steps, and each step has a small yield. So you go decreasing the yield. So you produce a high amount of waste. You have to purify the product all the time. So it's highly wasteful. So this is why in my PhD we approached pharmaceutical industry. Uh-huh. So I looked at two processes specifically. So one of them, we were making rose oxide, which is a fragrance that gives the smell of roses. It was really nice because the lab was smelling good for once. So I liked working with this reaction. But this is a multi-ton scale process. So it's done, it's the fragrance that is used the most in the cosmetic industry. And we can make it using a photochemical step. So we can make one, a key transformation using the energy of light. So this is in the scope of green chem because, we're using light, which is abundant and, doesn't and inherently like safer than, let's say, heating reactor or things like this. In another project I was producing like amines, which are molecules that have, lots of applicability to make medicines. For instance, they have a lot of activity in the nervous system. If you think of like methamphetamine, anything that we think about amine, they really have high activities in our bodies, and we could make them, but then it's a multi-step process as well. But what we managed to make it in a one step, and to really like use the bits of molecules that we leave that would be waste. We can incorporate them again, and like make the process more, like more one pot, like more efficient. Let's say more what we say in green chemistry. We talk about atom economy. So out of all of the atoms that you put in there, we try to incorporate as much as we can in the end, so that we don't have too much waste. You see?
Oh, wow. So basically, green chemistry can be used in any industry where there's a lot of waste. Oh, wow.
Yeah.
Where we can use. Sorry, go on.
Yeah. In my postdoc now, the group that I'm working on, so I just started, so I haven't really, worked a lot in their themes yet, but they are known for doing biomass transformation reactions. So they work with lignin, which is the part of food that is usually hard to work with, and they have methods to stabilize it, and then they can, extract very high value chemicals from this biomass that is usually waste. So, there's many ways that you can approach green chemistry differently.
Okay, interesting. Where we can definitely use green chemistry? I recently recorded, the movie Glass Onion, and
I probably know the movie in Portuguese.
Okay, probably.
But I know what you're talking about.
Yeah, but the content would be the same. So in that, they claim there is this clear crystal, which is like zero carbon emission, and it's like super cool, and hydrogen fuel, and da-da-da-da. And we recorded a podcast we recorded a video rather with like the science behind Knives Out, and in that one of the points was, it's ridiculous at this point, like as of today, making the hydrogen fuels or making the hydrogen fuel cells or this clear crystal. It's not environmentally friendly. I should not say that. It's not green. It's not like creating this crystal or synthesizing this hydrogen fuel is emitting a lot of carbon dioxide because we don't have any process. So I think that's where we will definitely need you and your group to step in.
Exactly, and this is really like something that we talk about in green chem as well. We talk about cradle to gate, that we try to think about our processes. So from the beginning, or when everything, the raw materials are sourced from nature, until when they are disposed. So this is like, ideally we should think about green chemistry looking at this whole process, but it's difficult for us to do the whole thing. So we try to break it up. So we look into specific steps, but ideally green chem talks about this whole process, like looking at where we source the materials and how they are disposed in the end. And we try to really do like smart chemistry. We have the resources, we have the tools. We have to put them together, in a smart way to make things work out. Yeah,
I mean it's really interesting for sure. So which are the industries? I mean, now that we have the expert on the podcast under the microscope, which are the industries which could use green chemistry sooner rather than later? You already mentioned the pharmaceutical industry, where 90% of the chemicals are disposed of and only 10% are useful or valuable. So which other industries are the ones which definitely could use some help of green chemistry or making their chemical processes more greener? Which other industries are there?
Yeah, so it's very broad to say to making them greener. So like every industry we can make the processes greener.
I know.
In different ways. I think like the pharmaceutical industry is the one that I focused a lot on my PhD really because it's screaming the amount of waste that they produce. And there's also like use of solvents, for instance. Most of the waste that we form in chemical reactions are from solvent use, which is insane because the solvent is not, like we usually don't think about the solvent when we're thinking about a reaction because the solvent is just there, theoretically assisting. But, it's usually most of the waste that we produce. So those are things that we look into a lot. There's, of course, the petrochemical industry, which is, incredibly efficient on the way they do everything. So those are reactions, that work very well. We have a lot of infrastructure for it. Theoretically, it's a very efficient process. There's not much waste or anything. The problem is like the raw material that we use, right? So every industry, we have to look into different aspects of it. Yeah.
Yeah, that makes sense. And now that you say it, when you said solvents, I was reminded of how much solvent we used when I was doing my master thesis, for example, or even PhD, but mainly master thesis, while cleaning the substrate. So we used like 250 ml of acetone 3 times, plus 250 ml of isopropanol 1 time. So it's just a lot, and we had like crates and crates or buckets and buckets of acetone, and we had buckets. And I know that acetone is probably not the solvent. That's not what you meant, but I'm just thinking from the chemicals.
No, but that goes into it as well. I mean, purification columns is just so this is why what I do like in my projects we usually do catalysis in a heterogeneous way, which means the catalysts are usually like solid, and heterogeneous just means that the catalyst is not in the same phase as the reaction media. In my case, I usually use solid catalysts, and I do the reactions in the liquid phase so that I can separate the catalyst by filtration or in some way. For example, I worked with magnetic materials, so I could separate them magnetically. So you don't have to run those columns to purify from from the catalyst, because the catalyst is usually like most times you use metals and like scarce metals, toxic metals, that they do a great job in catalyzing the system, but of course you don't want to keep them in there, otherwise they're going to be they're going to add toxicity to your system. So we need to find ways to separate. Heterogeneous catalysis is a good way to do this because the catalyst is solid. You can let it settle. You can track it like magnetically. You can filter, you can centrifuge it. There's many different ways to look into it. Yeah.
That's a very good point. And for everyone who does not or who hasn't understood what heterogeneous catalysis means, just to give like a very simple and non-relatable or relatable example, so to say, is that if you have water and if salt is your catalyst, water is your solvent, it's in liquid state, and salt is your catalyst, let's assume that. And so what you do, or what you could do as a heterogeneous catalysis approach, is like you dunk a giant crystal of salt in the water, so let a part of the salt be dissolved in the water to whatever extent, 5 minutes, 10 minutes, and then take the solid crystal of salt out. So that means it's easier to remove it instead of putting like ground salt, like the normal salt, in the water and letting it all dissolve. Does that make sense? Did I give a good example?
It does make sense, but I think a better example would be, let's say if you get like a fine salt and you put in water, it would dissolve. So this would be, like homogeneous catalysis. But let's say you use sand instead of salt. This would be heterogeneous. So if you use sand instead of salt, after you can separate the sand from the water.
That is good. Yeah, that's a good one.
Because
Yeah.
in the example you gave, when the part of the salt is like being dissolved, actually, like it would be homogeneous catalysis, because the salt that is actually doing the catalysis is the reaction is the one that is in the system. But those are boundaries of there's a lot of discussion on what is homogeneous or heterogeneous. But I think the sand example is good, because after you can separate it, there's no sand left in the system. You can filter it and or let it settle. Yeah.
Yes, thank you for explaining that. That's a very good point, because in my head, heterogeneous catalysis only meant that instead of using a liquid catalyst, you use like a solid catalyst in this particular example. But you're absolutely right. It's not just about that. The homogeneity goes beyond just the phase or liquid or solid or whatever.
Exactly. Yeah.
Okay. Wow. Oh my God. This is so cool. Oh my God. Oh my God. Oh my God. Julio, tell me, this is so fascinating. So how did you end up, now that you're in Switzerland, very close to me actually, in Germany, how did you end up doing green chemistry now, a postdoc in Switzerland? How did that happen? Tell me your life story.
Okay, so I'm originally from Brazil. I'm from a small village in Brazil, and then I went to a university that is close to my village, that is known for being like an agriculture university. It's traditionally, agriculture, but they have a good chemistry department, because agriculture depends a lot on chemistry, and they really have a mindset of sustainability in the university as a whole. So from the beginning, for my formation as a scientist, there was always the sustainability mindset throughout it. And then I started working just like in my second year undergrad. I started working in a lab where we did degradation of pollutants in water. And then it was it was super cool. And then it was like already like in my second year, so I had a lot of opportunities there, to be close. And it's a small university, so we're very close to the profs and very close to the grad students as well. So I was very exposed to all of this. And then I did it I had an opportunity to do an exchange during my undergrad, like in Canada, in Toronto. And then I did some different type of catalysis, but I wanted to have the sustainability mindset. So I was in a green chemistry related group. So I really like the idea, it's something that makes sense to me, and it's something that motivates me as a scientist to, think about that, there's like this huge problem that we're facing, we have to, there's climate change there, we produce too much waste, we have to, become carbon neutral, there's so many challenges. So it motivates me to think that that I can somehow use my knowledge to contribute to that. And then for my PhD, by the time I did my master's in a group that also did degradation of pollutants in Brazil, in kind of the similar line. And then for my PhD, I was already pretty sure that I wanted to work on this field. And because I knew how to do catalysis that I had learned, in my master's, I thought about, maybe let's look into the groups that use catalysis to do green chemistry. And then I found the group of Professor Morris and McGill, that they're really towards, green chem. It's like really the main theme of the lab. And Professor Morris was super cool. So I did an exchange with her during my master's, and we really worked well together. And then I went for the PhD at McGill. And during my PhD, I had every single opportunity to be in the green chemistry community. It's such a welcoming community, and everybody's so close. And I really like how the community is built, and we had opportunity to be with the big names in green chem, and I went to summer schools of like green chemistry. There's a big green chemistry initiative at the ACS that I went to everything they did. We have like the green chemistry conferences. So like, the community is very close, and we get close to people, and then we start to collaborate more, we start to learn more, and we start to be more motivated to be in the field. So everything just like went together. And then I was finishing my PhD. I was interested in keep working with green chem, but looking at different different parts of it, let's say. And then I found the group here, Professor Luther Bacher. They're doing super good work. I got in touch, and then I wanted to move around because I like to move around the world, So I did my PhD in Canada. I was like, now I have to go somewhere else. So yeah, so it worked out to be here, and I like it because green chem really gives me motivation, and I'm very cute. I love like nanoscience. I find it fascinating how we can control, like down to the nanoscale. How can we control nature in this way and make those weird particles, those weird shapes? I find it mind-blowing. So it moves me, the green chemistry motivation of it. And also I'm very curious about all of this. So I get to marry the two together. So it's pretty cool. I really like it.
That is so cool. I'm so happy to hear that. And I think you're like the definition of traveling scientist, because you have from the South America to the Northern America, and now you're in Europe. And I hope your next
I'm going to Asia.
Asia, yeah, and then Australia, New Zealand while you're at it, and then also the Arctic Circle, Antarctica. I see you going there, and I think honestly, I think at the North and the South poles, I never remember which one is north. Arctic is north, right?
The Arctic is north, yes.
Arctic is
Canada.
North and Antarctica is south.
Canada is the Arctic.
Canada is Arctic, exactly. And I think with so many expeditions happening there, I think we could definitely use our expertise as a green chemist over there. But that's a bit in future. Let's go with that. But I am with you. I also find it really fascinating, and I'm very happy that we have you on this episode of Under the Microscope, because green chemistry is something which whenever anyone says green or sustainable, the first thing that comes to people's mind is, oh yeah, renewable energy. But that's not what you mean. I mean, you can mean that as well, but
exactly, renewable energy is also green chem, but it's not only. Exactly.
It's not only renewable energies that is the green chem. So this is extremely important. And it's very nice to hear that the community, the green chemistry community, is like a tight knit community. Yeah. Definitely want to hear more about it after we stop recording. I don't want to put you on the spot here, that about the summer schools or conferences or something, because I definitely would like to have more green chemists on the podcast.
Mm-hmm.
On Microscope podcast, because we have had a bunch of people who are working with renewable energy in the renewable energy field, be it the hydrogen fuel cells or be it the battery research and But yeah, I would love to have more from the green chemistry perspective.
And I can give you a lot of names of people that are super cool that will love to be here in the podcast. And
awesome.
And what's cool as well is that when I did my undergrad, many years ago, we had the idea of sustainability in chemistry somehow, but at least in my university we didn't have a green chem course. We didn't have a program for green chemistry, so we kind of learned it on the go. So in my PhD, I was lucky to have the opportunities to go to the summer school and all of this when I got, more let's say more formal education about green chem and all of this. But nowadays, there's a lot of schools most schools, they do have a green chemistry course. So it's really nice. And there's also Beyond B9, which is a company that they help green chemistry education. So they, they produce a lot of resources from high school to like university level as well. They have like a green chemistry commitment that the universities sign, so that they, will get resources and they get support from Beyond Benign to, promote green chemistry education in their institutions. So it's really cool. Like we're seeing this movement, and we're seeing more and more green chem, because in the end, what we say is that ideally there should be no such thing as green chem. Like all chemistry should be green, because it's really something that spans all over. There's no because when people ask me like, are you an organic chemistry or inorganic or a physical chemist, I don't know.
Which type of chemist are you? Yeah.
But most times we don't know, right? Most times, even if you are organic, like you do a lot of like inorganic and analytical. Like who doesn't do analytical chem? It's just like it's difficult to define. But green chem really like spans all over the spectrum of chemistry, which is cool. Yeah.
That is absolutely right. It's almost like material science, which just goes into all the industries. Green chemistry is similar. It just goes into all the different industries. And yeah, you're absolutely right. And I agree with you. Every chemistry should be green chemistry. Or rather, we shouldn't have to create a niche field that is green chemistry. In an ideal world, there should just be chemistry.
Exactly,
And
which should be green intrinsically.
By nature. Yeah. It's like diversity and inclusion. We don't need to have diversity and inclusion. We should not need to have diversity and inclusion and equal opportunity and da. In an ideal world, in a perfect world, everyone gets equal opportunities. Everyone gets everything that anyone else gets, and they are not being excluded.
But since it's not like this, we do have to have the EDI people. And since not all chemistry is green, as we know, we do need to have the green chemistry people. But someday maybe we'll be a little bit better at all of this.
Yeah. Absolutely, wishful thinking. Yeah, absolutely. So until we reach the point where every chemistry is green chemistry, I want to know from you. It sounds to me that since your undergrad time and up until now, even like today when you're doing a postdoc in Switzerland, you have been involved in a lot of interesting research projects. I'm assuming, I have the feeling based on the examples you gave me. So I want to know, and this is a tough question, I know that, and I apologize in advance, but can you pick one research project that you're most proud of, or your most fun or quirky one, and explain it to us in the section we call In Other Words?
Yes, of course. So I do have one project that I really like and that I'm very proud of, which hasn't been published yet, but hopefully it'll be published soon. But the idea
about it?
Yeah, I can talk about it. It's on Chem Archive, so it's public.
Great.
The idea is that, so a funny thing is, during my master's, we found out serendipitously. How do you say this right?
Serendipity. By serendipity.
Serendipity, yes. We found out through by this that we were using like mesoporous materials to make catalysis. So materials that have pores that are so tiny that they are close to the sizes of the molecules. So
like a sponge?
You could make the analogy of being like a sponge, but I was using mesoporous silica, but it's structures that you can think about. Lots of straws together.
Straw. Okay.
Straws together, so there's lots of like holes, cylindrical holes, long ones. But imagine this like very, very tiny, so that the hole, in the straw is just a little bit bigger than the size of a molecule, let's say.
Okay, I'm with you. Okay, microscopic,
nanoscopic. Yeah.
Oh,
Yeah.
okay. Right, okay.
Yeah. Yeah.
Uh-huh.
So like very tiny.
Mhm.
And then, we found out chemistry happened very differently when it was inside those pores that were tiny, tiny, close to the size of the molecules than it would happen when they're on the outside of those pores.
So basically, what you're saying is that if we have a straw, then the chemistry, the chemical process inside the straw is different than outside on the outer layer of the straw.
Yes, yes. So let me give you another like an analogy that I really like that I usually give in my talks.
Tell
So
me.
you know the Little Prince,
Who?
the Little Prince.
Little Press?
The Little Prince, the guy, the French story of the Little Prince that lives in a tiny planet, and then he travels around.
I grew up in Asia, so we
Okay.
didn't have a Little Prince. But yeah, please go for it.
anyways,
Tell
anyways,
us the story.
if
It's
you just
story time with Julio.
if you Google, after if you just Google the Little Prince, you see, you've probably seen the cartoon, the drawings somewhere somehow. But the
Okay.
idea is that he lives in a very tiny planet.
Okay.
Okay, he's a little boy that lives in a very tiny planet,
Uh-huh.
very, very tiny. And then when you see the drawings, the his height is the radius of the planet. So the planet is not much bigger than his.
Oh, wow.
And it's very cute. And then he travels around the universe and eventually he goes to the Earth. But the idea is that when I was a kid, I would see this and I was surprised because his size is so close to the size of the planet that when he walks, you really see like him tilting, walking through the planet because the planet is so tiny.
Uh-huh. Uh-huh.
And when
Uh-huh.
he's in his planet, he sees everything. So if there's let's say, if there's a tree that starts growing, he has to cut it right away, otherwise the tree will become too big and will take over the planet. And like he has a rose that he really takes care of, and he's always close to the rose. So he's close to everything in the planet. If anything ever happens there, he sees it right away.
Uh-huh. Uh-huh.
And he feels the curve of the planet as he walks. So,
Uh-huh.
like it's a very different perception. When he goes to the Earth, he doesn't feel the curve of the Earth as he's walking, just because the Earth is much bigger than he is.
True.
And, and if you think all of us, we live on the Earth our whole lives, we never see the whole planet, we never see everybody who's in here, who would say at the same time. So, the Little Prince, he sees the world very differently when he is in his little planet versus when he's on the Earth. Just because his planet is not much bigger than he is, but the Earth is much bigger than he is. So you can think about the molecules. If they are in a space that is very tiny, close to their size, they will feel the walls of the, let's say, whatever place of the little straw they are in. They will feel the walls. They will interact a lot with the walls. They will see all of the other molecules that are in there all of the time. They will, shock with the other molecules all the time, which is different if they are outside of the straw, let's say, when they have a lot of free space. They will maybe not encounter the walls of the straw that much. They will maybe not encounter all of the other molecules that much. They can grow as much as they want. When they're inside the straw, they cannot grow too much, so they cannot form big molecules, for instance, inside the straw.
Right.
So everything is very different. So the idea is that chemistry happens differently when it's what we call confined. So if we put the chemicals in tiny, tiny nanospaces and we let them react, they will form different products than they would when they are not in those tiny, tiny nanospaces. And this is the idea. So I try to explore the fact of like confining the reactions inside those nanospaces. And I try to use this to make the reaction more efficient and more effective. So let's say I was working with a reaction that forms hydrogen. So we just talked about how difficult it is to produce hydrogen, right? That forms hydrogen and then uses this hydrogen to a second step in the same reaction.
Oh, wow.
So this is really good because you don't need to put a hydrogen source in there. You form the
Yeah.
hydrogen and you use it right away, in the same reaction.
It's like an ecosystem.
Exactly. The problem is that hydrogen is tiny. Hydrogen is a gas, so if it's not, if it like it can escape very easily, so you lose it. So what we did is like we trapped it into tiny nanospheres. So spheres that are so tiny that they are not much bigger than the molecules themselves. So when the hydrogen was formed inside the nanosphere, it would stick there. It wouldn't have that much time to escape because it would be shocking with all of the other molecules all of the time, and then you would have it utilized right away.
Right.
And this is something that I really found, and we found, that it's drastic how much the reaction changes when it's confined, when it's not. And we could study, like how big the space is, where we are confining and how this changes the reactivity. And this is really cool. And I think this is something that I don't know, like it blew my mind when we saw how much of a difference it made just, trapping them in there.
Even
So
the idea of it, I mean, now that you're explaining it to me, it's blowing my mind in
maybe I
real
went
like
through,
right
maybe
now.
I did like a long round to go through the Little Prince, but I hope it made sense.
It made a lot of sense. And while we were talking, I just very quickly Googled and looked at the picture of this little prince with the rose and a fox, I think.
Yeah,
Uh,
yeah.
and yeah, it makes a lot of sense. Oh my God. Wow. That is so cool. I hope your paper is out sooner rather than later
Me too.
because, oh my God. You have submitted it, right? Please tell me you have submitted it.
Yeah, I submitted it.
Ah,
Yeah.
okay, that's good. That's good. Then it will be out soon, hopefully soon, and then we will know all the more details, like quantitative details, like how is the rate of the reaction is better. And oh my God, that is so cool. Oh my God, oh my God,
It's really
wow.
cool when we can use this concept, and it's a concept that we can use for many, many different types of reactions we can study. There's like so funny thing is like during COVID confinement, so when we were like staying at home, I wrote a review about confinement of molecules.
I was, now that I was about to, I stopped myself from doing it when you were explaining, the confinement and the molecules outside. The first thing that came to my mind was like, it's like COVID. It's like during the pandemic and the lockdowns, how we were all stuck in our house
And you can
instead of
see that
going
we behave very differently when we are confined versus when we are not, just like the molecules.
Exactly. Oh my God. Yes. That's how nature works, even at a nanoscale.
Exactly. Yeah.
We behave differently, atoms behave differently, reactions happen in a different way when
Yeah.
you're confined in your four walls compared to when you go out and bump into other people, not
Exactly.
literally, or sometimes literally.
And
Um,
I'm not the one who found it out. There's like many studies about confinement effects already. But what we're trying to do, and what I did really in this review, is I tried to point out how confinement effects can make chemistry greener. So how can we use those and harvest this power to,
mhm.
to use it in green chemistry? So
Oh, wow.
so, in this example that I gave, we're really trapping the hydrogen in there, so we don't need to add extra hydrogen. And for the product is much more pure at the end, so we don't need to purify it that much and separate. So, there's a lot of like different things that we can tackle using this tool in green chem. So yeah, that's just
Wow, yeah, absolutely. Also, I see this like psychology aspect, like angle to it and philosophical angle to it as well. Oh my God, that is so cool. Please, link the review when you're curating the Real Scientist Nano Twitter account, and please go over it because I think this is so cool. Oh my God,
I will,
this is
I
so
will.
cool. This is so cool. So, okay, it's clear to me, Julio, that you love the research aspect of being a scientist. What else do you like about being a scientist?
I really, really love education. Actually, I got into chemistry because of education. because my dream was to be a teacher. My dream was to be a chemistry teacher. And then I went to a chemistry teaching program in my university. But then in Brazil, usually when you take like pure sciences like chemistry or math or physics, you usually have the chance to take both degrees, like the teaching and research together. And because I was there at the university, like I was curious, I started doing research, I kind of liked it, so I took both degrees together. And I have always been doing education during my undergrad. I volunteered in a lot of like NGOs that did education for like extra activities for kids and stuff like this, which is really cool. During my grad school, I loved TAing. It was just so much fun. I TA'd like the Gen Chem tutorials for like years, and I loved it. I had like so much fun. So education is really something that rings a bell to me. So this is what I like about academia, because I know it's not completely balanced, the value that academia gives to education and to research, right? Most of the times. But I like it that we can do both,
Yeah, absolutely.
So this is something that, like really motivates me, because I love interacting with people, I like the research. I love the motivation of doing this. I'm curious about it, but I think I'm mostly like a people's person. So I love to talk to people. I love to be with people, so like I love students because, we're talking all the time. We see them, like being interested about things. And I love this. And I love it too that, something else that I like about research, which is also related to to this interpersonal part of it, is that it's so global, it's so international. So like we interact with people from like all over the world. Look at us, we're here talking because of science. And you get to meet all sorts of people, very different people, more and more diverse, and we get to travel around. We get to live in different continents. We get to experience all these different cultures. I mean, it's something that I really like it's a lifestyle that I like. At least I've been enjoying, this time. Eventually I'll probably settle somewhere, but I'm enjoying it right now the way it is.
Yeah, that sounds good. I mean, I don't think, or rather, I don't want to see you settle until you have lived on all the different continents. So that's not happening anytime soon. 2 down. How many continents are there? 6, 4 more to go. I think there are 6 or 7 major continents in the world.
Yeah,
right?
I'm missing Africa, Asia, and Oceania. Yeah.
Exactly. Wow, my geography knowledge is really shit. Oh my God. But yeah, no, this is really cool, because we definitely need scientists who enjoy educating and they enjoy interacting, and they are more like people. People.
Yeah, I don't know how to say this, but yeah.
That, but no, I love that, and I love that. That is really cool. So, Julio, it has been wonderful, and I hope that your research experience so far has been wonderful. That's how it sounds like to me, at least. Of course, because you also only told us about the highlights. However, if you had 3 wishes to improve your research experience, what would you ask for? And I'm not promising anything here, okay?
2 wishes.
3 wishes, yeah.
3 wishes. In the chemistry field and STM in general, there's things that we could, 3 things that we could have more, which is more LGBTQ, more women, and more BIPOC people. I think those are 3 wishes. Is that too much to ask?
No, it's definitely not too much to ask. No, it's definitely not too much to ask. And for anyone who doesn't understand what BIPOC means, what does it stand for? Can you just explain it? Because it might be a new term for a lot of listeners. So
yeah, I don't remember what it stands for. It's people of color, Black, Indigenous, and other people of color. So it's basically not white people. Yeah.
Basically, diversity and inclusion.
Exactly. Yeah, I think it's something that, of course, academia is not perfect and research environment is not perfect. There's lots of things that we can improve. But I think, we generally, we have the conditions, at least, like in the places I've been to. I was lucky to be, like, let's say like in Canada and like here in Switzerland, places with like resources to do research. So those are very good things. What I miss more is like more people like me in the environments, our research, so yeah, I think diversity is the thing that we miss the most, at least from my perspective in science.
Yeah, absolutely. We definitely need more diversity. I'm with you.
More people like us. Yeah.
People like us, more people like us, absolutely. So, Julio, this has been wonderful. Please tell me. Last question, and then I stop asking you questions. When you're taking over the Real Scientist Nano Twitter account, what can the followers expect from that 1 week from Monday to Sunday?
Okay, so you will see green chemistry. You'll see a lot of green chem, and maybe maybe I'll share like resources on green chem, things that I really like. How to get more involved and how to learn more about green chem. You will see pretty cool nano confinement things and pretty cool, nanoparticle designs that I've been through, or things that I like in the literature. I will share with you guys some of it. We'll do some education as well, some links on education that I like, and of course, stuff on EDI as well, which is never too much. So, yeah.
Okay, so we are going to get a mixed bag of information and lots of education.
I hope we'll be able to deliver all of this, but
I'm sure you will. And just what I missed from that is pictures from the EPFL campus, pictures from the lake, pictures of the view of your office, and the picture of the Alps and the sheep as well.
Okay, so can I put that as well? Okay.
Yeah, of course. Of course.
Then you'll be pleased. I do have a lot of those.
Awesome. We want your coffee, your tea, your food, everything. We want to know everything about Julio in that 1 week. Everything, literally.
Because I just for context for like the viewers, I just got here. I started my postdoc like 2 weeks ago. And I'm just like, I feel like a tourist everywhere. So like I'm on campus and like stopping by, taking pictures of everything. And I'm walking around the city and I'm taking pictures of everything. It's the first time I'm living in Europe too. So like things are very different. So everything's like too exciting for me at the moment. Yeah.
That's awesome. Also in Lausanne, there is this Olympic museum or something, right?
I have to go. I haven't been there. Yeah.
To go, we need to see it. Absolutely. Just for us, you have to go.
Yeah.
All right, super. Thank you very much, Julio. This has been wonderful, and looking forward to having you on Real Scientist Nano. Thank you.
Yeah, so nice meeting you. Have a great day.
Abstract submission for the 6th Nanoscientific Forum Europe 2023 is now open. Join this European SPM meeting and be part of exciting talks from the nanoresearch field, practical hands-on sessions, and a thrilling social program in Barcelona's Flair, hosted by ICFO, Barcelona, Spain. See you in Barcelona in September 2023.